In this last question, we're going to look at a swimming situation. It says a swimmer named Amy specializes in the 50-meter backstroke. In competition, her mean time for the event is 30.5 seconds. So we will write that down. And her standard deviation was 0.5 seconds. Assume that Amy's times are approximately normally distributed. So we're going to go through, now there is a thing about swimming times where like faster times are worse, but we're still going to put the faster times to the right on the normal curve and the slower times to the left. So it says the next time Amy raced, she finished in 30.2 seconds. What was the z-score of her time? So to set up that z-score, we want to take the value that's given, which is 30.2, subtract the mean, which is 30.5, and divide by the standard deviation. So that's going to give me negative 0.6 for the z-score. We're pretty close to the mean, right? We're not even one standard deviation away, and it is below that time. So the next one, when Amy raced again, she finished in 32 seconds. What was the z-score for that time? So same deal. We have, now it's 32 minus 30.5, value minus mean over standard deviation. And this one has a z-score of 3. So that's pretty far to the right? Pretty far from the average in that direction. Now we're going to find the race time that has a z-score of negative 1.7. So when I set this one up, now I know the z-score is negative 1.7. We are going to find the value, so I'm going to put an x in for that, minus 30.5 over 0.5. Here I can cross multiply. So negative 1.7 times 0.5 is negative 0.85, and that equals x minus 30.5. So we're going to add that value over. And that's going to give me a value of 29.65 seconds. Okay, so looking at the next one, we're going to give a range of race times for Amy centered around the mean that would be expected to occur 95% of the time. So we should start to be heading towards to knowing that that means from negative 2 standard deviations to 2 standard deviations. So over here, I'm going to take my mean and subtract 2 standard deviations. And that is going to give me 38.5. And then I'm also going to add 2 standard deviations. And that's going to give me 40.5. So that range is from the expected race times, right? The ones that usually occur are from 38.5 seconds to 40.5 seconds. And on my curve, we're going to label those values. This is where the 38.5 would go, and this is where the 40.5 would go. So the next question has to do with baseball and softball. Says nope, that's on the homework. This one has to do with car tires. The distribution of lifetimes of a particular brand of car tires is approximately normally distributed and has a mean of 51,200 miles and a standard deviation of 8,200 miles. So we'll write down our statistics that are given. Jessica buys a pair of these tires and they only last 34,000 miles. So that is our value that we're going to be looking at in this problem. It says find the z-score for the number of miles Jessica's tires lasted to the nearest 10. So setting up our z-score formula, value minus mean over standard deviation. And if I type that in, that's going to give me a z-score of negative 2.1. So follow-up question, Jessica believes the tires may be defective. Explain how she could argue that her tires lasted for an unusually low number of miles. So the way we can argue with this, we can say, since the z-score is less than negative 2.1, or sorry, negative 2.0, right? That's our cutoff for usual between negative 2 and positive 2 for the z-scores. The tires lasted an unusually low number of miles and could be defective. And I would say, we could say they're probably defective once we get outside of those values. I skipped part of part A. I was supposed to explain what the value means in the context of the problem. This means her tires lasted 2.1 standard deviations below the mean value. Last one, Luke bought the same tires. His tires lasted for a number of miles with a z-score of negative 1.5. Find how far his tires lasted and explain why he does not have a reason to believe the tires are defective, even though they did not last as long as the average. So we'll find his value first. Z equals the value we're looking for, minus 51,200 over the 8,200. Now, this is a pretty simple equation to solve, so I'm just going to write down the answer just to shorten the video a little bit. If we solve that equation, we would get 38,900 miles. Now, that still stinks, right? His tires did not last as long. He's probably, annoyed that he has to buy new tires. But this question about why he does not have a reason to believe the tires are defective, right? We're expecting some variation. And since the z-score is within 2 standard deviations of the mean, in other words, since the z-score is in between negative 2 and 2, so I'll put that in parentheses, okay? It is not an unusual value.